The Cowboys won, so we're having a quiz today. No, you you have something to turn in, right? So please, if you could get that up here, please. How did that go? Oh, that looks good. That looks real good. All right, awesome. Very good. It's okay. Just keep it all together. It's good. It's okay. All right. Well, we're down to 3 class meetings. Is there anyone else? Quiz? That's okay. Just put them together. I should be able to keep track of it. All right. So we have 3 more class meetings, right? 3 more. And one of those is going to be reviewing for the final, which, oh yeah, I have those tests, anyone who didn't have them last time, but get them at the end if you could. Let me just look at the calendar. Our final is on Thursday, December 12th. So we'll have our last day that we meet. Whoa, wait a minute, hold on. Uh-oh. I kind of messed this up a little bit on my schedule. I just realized this. I better write this down so it's documented. Thursday, December 5th is the last day of class, okay? That's the last day that we meet, and on that day, we will review for the final. Oh. Yeah. Then on Tuesday, December 10th, there's no class. On the schedule, it says that we review on that day. But that's finals week. So in finals week, you should only meet one time with your class, and that's for the final. You shouldn't, you normally meet 2 days a week. You should only be meeting one day. And for us, it's not on Tuesday, it's on Thursday. Thursday, December 12th. We will have our final exam. It will be at 9:30 a.m. and it will end at 12:15 p.m. Make sure you're aware of that time. All right? Questions on that? Okay. Just make sure you don't show up on this Tuesday and say, "Oh, I showed up, I was going for the final review." We're not doing it. We're doing it on that Thursday, December 5th. So the real question is, how much more material do we want to cover? Right? So, we'll talk about that when we review. I'm thinking it might be just very little bits and pieces from the beginning. Nothing like, I don't think I'm going to have you graphing rational functions and polynomial functions and those things that took like 30 minutes to do. I doubt we're going to do. Because y'all did real good on that test. So, 10 factoring problems? All right, so look, exempt final, Interesting concept. Oh yeah, the cool professor you have? All right, so I'd like to cover two more topics, all right? Yeah, I don't know if I'm going to be able to do it though. So I want to show you elimination. Okay, we talked about how to solve a system of equations using substitution. So remember this? I give you a system of equations that would look like this: x plus y equals 10, negative 2x minus y equals negative 5. That is a system of linear equations, not inequalities, right? So this is not like your homework, your quiz. These are equations. So when we look at the solution to this, we're actually trying to figure out where two lines intersect each other. We're trying to find that point, right? Now the way we did this is I gave you that method called substitution, where you would go through all those steps, right? And I'm not going to go through them, but you would solve either of the equations for one of the variables you got to pick, and then, remember all that? Okay, you should have done that for your quiz. You had to do it somewhere in there. There was another method called elimination, which I'd like to show you. So, elimination. The way elimination is going to work, and I'm going to do that same problem, okay, x plus y equals 10, negative 2x minus y equals negative 5. The way I'm going to do it is by giving you the set of steps like we did last time, and then doing the step next to it, right? So what I'm going to do first, step one in this process of elimination, step one, is to look at both equations and see if either variable, and what I mean by that is x or y, would cancel if you added the equations together. All right, what the heck do I mean by that? So what I'm going to do for step one is I'm going to look at those two equations up there, and I'd like to see, let me look at my x's first. I have x, and then the other one is negative 2x, right? If I were to add those together, would the x's go away? What's x, and then add negative 2x? Or in other words, x minus 2x, what's that? Negative x. So it didn't go away, did it? Right? So the x's don't go away if I add them together. How about the y's? Y and negative y. If I add those two together, they go away, don't they? Okay. So I look at them. That's the first step. I look to see if anything would go away if I add them together right now. Right? They do. So if they do, that means one of the variables will cancel. I meant to say if they do. That means one of the variables will cancel. Then add them together. Then add both equations together. Okay, you ready to see this step? I'm going to take both equations and add them together. So I'll do this in blue underneath this as like my first step. Is that all right? Okay. So for step one, what I would do is I'd say, oh, look, my y's will go away if I add them together. So I take my x plus y equals 10. I take my negative 2x minus y equals, what was it, negative 5. And what I do is I add straight down. Okay, add straight down. If you add straight down, you get, what did we say happens with the x's? You get negative x plus nothing, right? 0 equals 10 minus 5 is 5. So negative x equals 5, right? And so what I really have is this, negative x equals 5. Divide both sides by negative 1 or multiply both sides by negative 1, you get x is negative 5. Do you see what I did? Now, I have an answer, don't I? I know what x is. For some strange reason, that was a little too easy, wasn't it? So what we do now, once we know what x is we go back and get y. So we're going to plug it in, but plug it in where? It turns out it doesn't matter. You can go either way. Either equation works. Okay? So what we're going to do now, this would be the next step, okay? Now look, I'm kind of working within this framework. If they do, we wanted to add both equations together, right? Then after we add them together, I'm going to add a little something to the end of this. Plug that answer back into, plug answer back into either equation. So I'm going to choose to use the first equation. All right, I'm just going to choose. So I'm going to take that first equation, x plus y equals 10, and I'm going to replace my x with negative 5. So I get negative 5 plus y equals 10, and adding 5 to both sides, y is 15. You agree? So as an ordered pair, negative 5, 15, right? We write the x, then the y, is the solution to that system of equations, or it's the intersection of those two lines. Now we could check it real quick, couldn't we? We could? Like take those two and plug them into the first equation. X plus y is 10. If I add an x and y together, do I get 10? Yes. The other one is a little more tricky. I'd have to go negative 2 times x, which would be negative 2 times negative 5, which is 10. Then minus 15, that would give me negative 5. So it works in both. This is pretty nice, right? Elimination. That's it. But the question would be, though, what if when we look at them and we try and add them together in the beginning, nothing cancels, right? Like this was real nice because the y canceled, right? What if it didn't? So that will be what we look at now. Let's take a look at another problem, okay? And I'll continue because right now our step one on this is basically look, see if they cancel. If they do, add the two equations together, plug that answer back in, we're done, everyone's happy. But what if we look at it and nothing cancels? So let's continue that note. If nothing cancels, then multiply one or both equations by something, which makes a variable cancel. All right, what the hell? So if I look and they don't cancel, then I'm going to make it cancel. But I have to be very careful how I do that, all right? So you ready? I'm going to give you a new example. As an example of this, let's see here. 3x minus 2y equals 1. And how about 4x plus y'all seem pretty sharp. I'm going to just go with this. 3y equals 7. Most of y'all. All right, so look at this right here. The method that we've learned in the past, substitution, right? Remember? Not today's method, before. What we did was we said, look at both equations, pick one variable, you get to choose, right? From either equation, and try and pick the nicest one. Would you agree that that substitution method that we had before isn't really nice for this? Like there's no nice, easy thing to pick. They all have numbers in front of them. Also, if I try and look by adding right now straight down, does anything cancel? No. So I've got kind of the ultimate whammy here. There's nothing that's just right there. So this note says, okay, if they did cancel, then I would just add them and I'd be done. If they don't, what I need to do is I need to multiply one of the equations or possibly both equations by something which will make one of the variables cancel. So right now I have to choose which variable do I want to make cancel, and it's totally up to me. In either way will work. It's just sometimes one's easier than the other. So just for this example, I'm going to try and make the x's cancel each other. But right now, if I add them, I get 7x, right? So what I need to do is try and multiply each equation or one of the equations by something to make them cancel. Remember with equations, you can always multiply an equation by any number, right? Both sides of the equation. So I'm free to take that first equation and multiply it by anything I want. So watch what I'm going to multiply it by. I think this first time you have to see me do it, and then you'll understand why. I'm going to multiply it by -4. Now, when I do that, the -4 has to pass through every term like this, right? What is that going to give me for my x term? -12x. Which means, what would I need to turn the 4x into so that when I add it down, they go away? I need to multiply it by 3 so that it would become a 12x. Do y'all see that? Multiply this bottom one by 3. That would give me a 12x. Then everything else, I'm just going to have to figure out what happens. They do not have to be both by the same number. They can. That's right. They have to be common multiples, right? So when I looked at this and I said one of them had a 3 and the other one had a 4, I used the opposite number for each one, for each equation, right? For the 3x, I used the other one's number, and for the 4x, I used the other one's. But I need to have them be off by a sign, so I made one of them negative and the other one positive. You could have done +4 on top and -3 on bottom. It would have also worked. So what I'd like to do now is draw an arrow, and I'd like to draw what we call the new system of equations by distributing through. So I should have -12x, then what? Plus 8y equals 4, -4. And then 12x plus 9y equals 21. Now, this is a new system of equations, all right? It's a new system of equations. Now, it turns out that by doing that, we haven't changed the answer. Whatever the answer was, it has not changed. So now look at this. If you add straight down, will one of the variables cancel? Yes. So now I see that my x's will cancel. So go ahead and add straight down. What do you get when you add straight down? You get 0 plus 17y equals negative 4 plus 21, right? Everything gets added down. 17. Which means 17y equals 17, which means y is 1. Dividing both sides by 17. We good? Now what do you do with that answer? Plug it back in. Now the question becomes, where do you plug it in? It doesn't matter. You can actually go into the first equation we had there, the second equation, or even any of the equations that we transformed. Any of those blue, you can plug that y equals 1 into any of them, and it should give you the answer for x. You can do it to what? No, because you have to plug it into an equation that has x in it, because we want x. So you're going back and trying to find an equation that has x in it. I'm just going to grab this first one here. I'm going to take that one right there, and I'm going to take 3x minus 2y equals 1. I'm going to substitute in for y the value 1. And you should get 3x minus 2 equals 1, which is 3x equals 3, which x is equal to 1. Okay? So you get 1, 1. That's it. So what do y'all think of this method? I mean, it's really up to you. And you know, sometimes the other method's a little bit nicer, sometimes this one is. It just depends. Let's do one more real quick. Ugh. What is that? Those are all decimals. The 4, yeah, the 4 does not have a decimal in front of it. I wanted to give you a problem like this just to get you kind of used to the idea of, well, not every number in the real world is nice, so here we go. Most of you don't want to work with decimals, which I understand. So the first thing I'm going to do is I'm going to eliminate all decimals. And to eliminate all decimals, how do you move a decimal point? How do you move it, though? Multiplying it by 10, right? If you multiply a number by 10, it moves the decimal point 1 to the right. I'm going to want to multiply each equation by how much? 100, because I'm going to move this 0.75 twice and this 0.35 twice, right? That means every decimal point I see is going to have to move to the right twice. Even on that 4, where's the decimal on the 4? It's the bottom right of it, right? That 4 is really like a 4.0. So everything moves to the right 2 places. But technically what we're doing is we're multiplying the top by 100, bottom by 100. Let's just do that to get rid of the decimals. What should we get? 30x minus 400y equals 75. And then 2x plus 80y equals 35. All right, now we are back to a system with no decimals, so it's not as bad. Let's try elimination. If we add straight down, does anything cancel? No. Anybody want to tell me how we can make them cancel? Okay, good. You can do just one equation. It doesn't have to be both. You could go close 15 or negative 15. So look, I've heard 2 different ways and they're both correct. I'm going to show you both side by side. You could take this 30x minus 400y equals 75, 2x plus 80y equals 35. You can get the x's to cancel by multiplying the bottom by negative 15, because that would give you a negative 30x, and that would cancel with your 30x, right? That's one approach. The other approach that I heard that is also correct is to go after the y's instead of the x's. And to do that, you would have to multiply the bottom equation by 5, because that 5 times that 80y would be what? 400y, and it would cancel with the negative 400y. Y'all see that? Or the negative 15. Okay, see if you can do it. Go ahead, multiply through. Do either one, whichever one you're happier with. Do that. Multiply. Remember that number, though, multiplies through the whole equation, though, right? The whole thing. And then add down and then plug back in and see what you get. Yeah, if you need your calculator, that's okay. By the way, these answers may not come out to be nice. They may be decimals. I'm going to get a decimal, and you should do the same. Anybody get 6.25 for x? Okay. So that's the work for it. I did it one way. Did anyone do it the other way? The one on the right side? Did y'all get the same answers? Okay, good. Any questions? You should get, your answer should be the ordered pair, 6.25, 0.28125. So this is like the first problem I've given you where the answers are not nice integers, right? They're decimals, which could happen. Are we good? Okay, that's it. Now I want to change something because on the notes here at the very top, I did the title of today's notes is Systems of Equations, 3 Variables. I'm going to change it. We are not going to do that. We're doing Systems, Equations, 2 Variables, and then we're doing Elimination. Right, that's what we just did, okay? I decided I'm not going to do 3 equations. But what I will say is, once you go to trying to solve, right now we had two equations with 2 variables, right? 2 equations, 2 variables. If we go 3 equations, 3 variables, you cannot use substitution, which was the first method I showed you. You have to use elimination. Well, I shouldn't say have to. Elimination is much easier than substitution. When you have 4 equations and 4 variables, elimination, not substitution. 5 equations, 5 variables, 6, 6. Okay, and you can have as many equations as you want with as many variables as you want. One of the biggest breakthroughs once computers were created and started, people started working with computers, was this guy who came up with the solution to this problem for financing, and basically tells insurance companies how to make their rates and stuff like that. The equation that he had to solve was 40 or 50 equations, 50 variables. And he was able to solve it using elimination. But it gets so tedious that the computer can do all this, look at 2 rows, try and get the variable to cancel, multiply the row. The computer can do all that really quick. So we actually have an algorithm for elimination. All right, we're going to move on, though, to our this will be our last topic of the semester, okay? And we'll pick up on it next week on Tuesday. We'll finish it up. No tears, please. Last topic. Now, this is a completely new topic, all right? Sequences and series. All right, sequences and series. In my Calculus 2 class right now, we are finishing the chapter on sequences and series. Today, I'm finishing that chapter. We've been in that chapter for 5 weeks, okay? We are not here today in this class to try and cover anything close to what sequences and series is in a calculus class. The goal of it here is to expose you to the notation of these things called sequences and series, all right? That's all it's about. So, but because of this, I do have some stuff from my Cal 2 class that might help us see what a sequence and series is, all right? Maybe. Where is it? Where am I looking? Well, you know what, before I bring it up, let me do this. Where are all my pens? All right, right now, if I wrote this down, and remember, I want you to clean your brain off, just get all that, the whole thing of systems of equations and inequalities and shading. Get all that out of your head and just start from scratch here, okay? If I wrote down f of x equals the square root of x, we would say that that's a function, right? And when we talk about functions, we talked about domains, things you can and can't plug in, right? I could take something like 2 pictures here, and I could talk about the function like this. Remember, we've done this, right? You plug in 0, what's the square root of 0? 0, right? Plug in 1, what's the square root of 1? 1, right? 4, what's the square root of 4? 2, right? What if I plug in negative 4? Can't do it, right? I can't take negative 4 over. I can't do the square root of a negative number. Well, but we don't, because we can't graph an imaginary number. So this would not be in the domain. Now, let me ask you this. Can I plug in here 1/4? Can you take the square root of a fraction? Sure. Could I plug in here 3/8? Sure, and then square root it, get your calculator out, whatever, we have a square root. Could I plug in pi? Square root of pi, we could do that, right? As long as it's 0 or positive, we can do it, right? And so when we graph this, it looked like this. When you graph the square root, that was one of our toolbox functions. Remember that? That's what the square root function looked like. So for every number, for every x value here, I'm highlighting my x-axis. For every x value I pick, I had some corresponding y value, which gave me a point on the graph, right? And that happened for every x to the right of 0, right? For every x, there's a y. For every x, there's a y. That is a function. We know that. Now let me describe to you what a sequence is. A sequence is the same thing as a function with one small exception. Other than that, though, it's exactly what we've been studying. A sequence is a function, but the domain, and the domain is what you can plug in, right? The things that are allowed to be plugged in, is restricted to positive integers only. What are the positive integers? In other words, what are the numbers? If I say, give me a positive integer, what are all the positive integers? 1, 2, 3, 4, right? Forever. Now, those are braces around that set of numbers. Those are the positive integers, 1, 2, 3, 4. So the sequence is the same thing as a function, but when I go to grab numbers to plug in, the only thing I can grab are the numbers 1, 2, 3, 4, 5, 6. That's the only place I can grab from, okay? I cannot grab pi, it's not there. I can't grab 1/4, it's not there. Can't grab 3/8, it's not there. So we've cut our domain. Does that kind of make sense? Can you what? Well, when we first start off with sequences, we say, no, you can't grab 0. Later on, we're allowed to shift this domain over. It always has to be integers, but we can shift it, and start at, let's say, from 3 on, or from 10 on, and you can even go backwards. But for now, let's just say from 1 on. That's the easiest way to get your head around this. Okay, so here's the way I would like to write this instead. As an example, I'd like to take that function that I just took, f of x, and instead of calling it f of x, I'm going to call it f of n, square root of n. Now, I need to tell you somehow that you are not allowed, let me put example above this, I need to somehow tell you that look, you're not allowed to plug in 1/2 into this. That the n that you plug in there has to be an integer. So how do I say that to you? Well, I say it like this. N is an element, so that's like a little e. N is an element of Z script plus. Now, have you all seen this before? R script R? What did that represent? All real numbers, right? That was all real numbers. That was like negative infinity to infinity. That's what that meant? Well, we have another special script letter. It's script Z. Script Z is all integers. But even 0 and -1 and -2, so it's all of them. So by putting a little plus in the top right of that Z, it says all the positive integers. Does that make sense? Z is a positive integer. Okay, so somebody give me something I'm allowed to plug into this. I could plug in 7. Something else? 1, 2, 3. Anything, right? The question, though, is what does it look like if I try and graph it? Because it does not look the same as the function that we had above. Because we're only allowed to plug in 1, 2, 3, 4, right? 5. So what would happen when we plug in 1? What would we get out? What's the square root of 1? 1. So we get a point, don't we? What happens when we plug in 2? Square root of 2, we get a point, don't we? Square root of 2 is like 1.41 something. Square root of 3 would be something else, right? You do it on your calculator. Square root of 4 would be 2. Do y'all see that? It looks kind of like this. But I cannot draw that red line in there. Curve. Why? Why can't I draw the curve in? Yeah, it's a function. But when we drew the function earlier, remember what I was saying right here, top right? I was saying for every x, we could take a square root and get something. So when we draw that curve, the curve represents all the little points. With the sequence, we do not have a curve. We have a bunch of dots scattered out. Only dots. So it does not, you can't draw it. You can't draw it without picking up your pencil. You just dot, 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 and don't connect them. Exactly. Okay? Do y'all see the difference? Now, let me give you just a real little insight into how this comes into play later. A lot of this is connected to statistics. All right, statistics. Think about there's two types of what we call variables in real life. One variable, for example, would be the number of students that show up to class on a given day. Right? Let's say that I listed out for every day this semester, for every day, I listed out how many students came to class, right? I'd have like, maybe 26, then 25, then maybe 26, then I would have these numbers, right? Is it possible to have day 1.5? No. So I can't talk about day 1.5, right? Is it possible to get an answer that comes out that's not an integer? No, right? So if I were to graph this, day 1, I would have so many students, day 2, so many students, but I would not have anything in between, would I? Do you see the difference? Do you see what's going on here? Those are called discrete random variables, where they take on integer values. The number of people that show up at a Spurs game, however many thousand, you don't say, 0.2. You don't have someone just with their arm show up, right? You know, you have to call a whole person as a person. So you don't have anything in between. Does that make sense? Can somebody give me an example of a variable that would not be an integer? So I've given you like the number of students that show up to my class Spurs game. I'll give you one because I see a McDonald's cup right there. You go to McDonald's, you ask for whatever, 32-ounce drink, right? They fill it up. Boom. Well, do you think if they fill it up, it has exactly 32 ounces in it? No. And the next customer gets a different one, it's different, right? It's not exactly 32 ounces. So if you were to take a sample of 100 cups that are supposed to be 32 ounces, the first one might be 32.5, the other one might be 29.7. The values that it can take on are not integers. That's called continuous random variables. So the way that we study continuous random variables like the soda involves curves that you can draw without picking up your pencil. The way we describe and study things that involve integer values, we use sequences and series, which is what I'm getting you introduced to. All right? That's just background of why we're doing this. All right, so let's go back to this example that we had here. We had f of n equals the square root of n, right? Now, I had to write this down to let you know that I wanted you to only pull positive integers, right? That's what I had to write. So what we did as math people is we said, this is a little too confusing. Instead, let's just use a different notation. Instead of writing f of n like that, we'll write something else to let people know that you're only going to pull positive integers. So this is what we write. A sub n equals the square root of n. This is the new notation. This is what we will use from now on. What I want you to see here is that the A is like the F. It's the name of the sequence. The N is just what's going to get plugged in. So tell me then, what's A sub 1? Square root of 1, which is 1, right? What's A sub 2? Square root of 2. I don't care what that is. What's A sub 3? Square root of 3, and then A sub 4 is square root of 4, which is 2. And I could keep going, couldn't I? Yes, they would. So that's why I'm not going to write them. I'm just going to leave them in the exact form. Questions? Now, let's look at our answers that we just got here. We had 1, we had square root of 2, we had 3, and we had 2, didn't we? If we look at that, that is a sequence of numbers, isn't it? It's a sequence of numbers. And that's where the term comes from, sequence. It's a sequence of numbers. So if I write it out a different way, watch this. Things can get a little tricky here. What I can do is this. I can say A sub n equals the sequence 1, root 2, root 3, 2, ... forever, close the brace. ... means repeat that pattern forever. Does everyone agree that 1, root 2, root 3, 2 is a sequence of numbers? That sequence is generated by the formula up here in blue, isn't it? That blue formula creates that sequence of numbers. Agreed? Crickets? Y'all okay? What I'm going to do right now is, in the next example, I'm going to give you a sequence, like a list like this, and I want you to give me the blue. So I'm going to write out a sequence of numbers. There's going to be a pattern in them, And I want you to tell me what that pattern is and go back and get that. So like right here, I would have to realize that this is the first term in the sequence, right? The first one? The first one, this is my A sub 1, this is my A sub 2, this is my A sub 3, this is my A sub 4. So I have to realize when I plug in 4, I get 2. When I plug in 3, root 3. When I plug in 2, I get root 2. Plug in 1, I get root 1. Do y'all follow that or not? Okay, let me give you an example and see if you get it. Example. Find a formula for a formula A sub n for this sequence. Sequence. Here we go. 2, 4, 6, 8, 10, ... forever. Anybody recognize those numbers? They're all positive, but they're evens. Those are your even numbers? Those are evens? So what sequence would create all the even numbers? So think about it. This first one right here should be what we get when we plug in 1, shouldn't it? The second one, 4, should be what we get when we plug in 2. This one should be A sub 3. This should be A sub 4. This should be A sub 5, right? So what are we doing? How do we get from 1 to 2 and 2 to 4 and 3 to 6 and 4 to 8 and 5 to 10? Multiplying by 2, right? We're just doubling whatever that subscript is. So A sub n should be what? 2n. That's your formula. Do y'all agree? A sub 1, if you plug 1 in down here for n, 2 times 1 is 2. You plug in 2, 2 times 2 is 4. You plug in 3, 2 times 3 is 6. That seems straightforward? We'll see. How about this one? Same instructions. Find a formula for 1, 3, 5, 7, 9, ... What are those numbers? Your odds. This one's a little bit tricky. Remember, the first one here is what you get when you plug in 1. The second one's what you get when you plug in 2. Third one's what you get when you plug in 3. Then 4. Then 5. Anybody have it? Let me tell you that this is, there's nothing I can teach you to make you see this. All right? You either see it or then I explain it and then hopefully you see it after I explain it. But the students in my past that have seen this, I always ask them, how did you see it? I don't know, I just saw it. There you go. That's it. What is it? Times 2 minus 1. See, isn't that list of numbers just your even numbers, but take 1 away from each one? Isn't it? Isn't every single one of those just like, you know, the 1 is really that 2, take 1 away. The 3 is that 4, take 1 away. So it should be that formula we had before, take 1 off each one. How do you see that? Yeah, exactly. 2n minus 1. 2n minus 1. Do you all see that? 2n minus 1. These are very important sequences. I mean, now that it's on the board, though, do you see it? It's all your evens, take 1 away. I'm starting off with the two very fundamental sequences. The sequence that creates all evens, the sequence that creates all odds. Now let me see if you can push a little further here. How about this one? How about if I want to go 6, 8, 10, 12, do you recognize 6, 8, 12, 14, 16, 18, 20? Those are still evens, aren't they? But you're starting at 6, not 2. Where did our list start earlier? Where did our sequence start before? At 2. So we already know how to create this one. 2, 4, 6, 8, 10, right? We know how to create that. We just use 2n, don't we? So instead of having a 2, what do I want? A 6. And instead of a 4, I want an 8. And instead of a 6, I want a 10. Instead of 8, I want 12. What's the common thing happening there? I'm adding 4 to that green list. I'm adding 4 to each one of those. What it's doing is it's taking this entire list here on the right. It's shifting every number by 4. If I add 4 to each one of those, I get that list, don't I? So 2n plus 4. Now, the good news is you can always check it, right? You can check your answer here. Plug 1 in. What would happen if you plug 1 in? 6. Plug 2 in? 8. Right? How about this? This is not meant to be tricky or anything. 5, 10, 15, 20, 25, 30, 35, 40. 5n. That's it. They're just multiples of 5. A sub n equals 5n. Plug in 1, you get 5, 2, 10, 3, 15, 4, 20. We're there? Hey. Now it all makes sense. All right, what do we got here? That falls apart eventually. We need that when we plug in, this one's tricky. When we plug in 1, we get that. When we plug in 2, we get this. When we plug in 3, we get this. 4, we get this. 5, we get that. Does anybody recognize what each of those numbers are? They're all multiples of 3, but, well, 3 is not a multiple of 9. I agree they're all multiples of 3, but get your head out of multiples. Think of it a different way. They're all somethings of 3, but not multiples. Kind of. Three is 3. How is 9 related to 3? 3 times 3. Okay, what's 27? 3 times 3 times 3. And what's 81? 3 times 3 times 3 times 3. So That's right. 3 raised to something gives, so each of those are powers of 3, right? Let me start with 3. It's 3 to the first, then 3 squared, then 3 cubed, then 3 to the fourth, right? That's what we have. But what about that first one? What's 1? Is that a power of 3? 3 to the 0. Good. Right? Is that right? Now, look, I need this to be my first term of my sequence, this one my second, this one my third, this one my fourth, and this one my fifth. Do y'all do y'all see that? Do y'all see the connection between things here? Like, what never changes? The 3, right? The only thing that changes in each of those is the power. The problem that I have is that when I plug in 1, I'm supposed to get a what as the power? 0. And when I plug in 2, I'm supposed to get 1. And when I plug in 3, I'm supposed to get 2. And when I plug in 4, I'm supposed to get 3. And 5, I'm supposed to get 4. So isn't it the power is always 1 less than what I plug in, right? So my formula should be A sub n equals 3, what do you mean 3n? Like 3n? 3 raised to the n minus 1 down here, minus 1 up there. Yes, that's it. 3 to the n minus 1. Do y'all agree with that formula now? This is actually what we call a geometric series. A geometric sequence. All right, well, we're running out of time, but let me challenge you a little bit more here. These are like puzzles, huh? Trying to undo these. Okay, how about this? Negative 1, 1, negative 1, 1, negative 1, 1, negative 1, 1, forever. Continue that pattern. We're going to wind up calling this an alternating sequence because it's alternating signs, isn't it? It's negative then positive, then negative then positive, then negative then positive. So the first one, A sub 1, should be negative 1. A sub 2 should be 1. A sub 3 should be negative 1, and so on and so forth. Anybody have any idea? I'll give you a hint. A sub n equals. I gave you half the answer. You just have to come up with the other side. Okay, what is it? Did you say negative what raised to n? There you go. That's it. Negative 1 to the n. What is the property? What is the property of negative 1? Think about negative 1. If we raise negative 1 to the first power, it's itself, right? But if you square it, it's positive. But if you cube it, it's negative. And if you raise it to the fourth, it's positive. So anytime it's odd, it's negative. Anytime it's even, it's positive. Do y'all see that? Yeah? Okay, so if you see that, then maybe you can see this. How about this? Well, 1 raised to the n is just 1. Because 1 raised to 1 is 1, 1 raised to 2 is 1, 1 raised to 3 is... That's going to give you the reciprocal. Now think about this. All you want is the same thing you had before, right? We want that same list that we had before, but we want to start with a positive, right? So couldn't I use the same exact formula that I had before and just, yeah, we can either start with 2, or can't we just throw a negative in front of it? Wouldn't that change everything we had? Like, what I'm saying is, why don't we take -1 and multiply it times the formula we just had? Right? In the yellow is the formula we had just a second ago. And that, well, that's what you do right there. That right there is, the yellow is the previous formula, which starts at -1. But now if we multiply it by -1, it becomes +1. Well, I'm not done. What I'm going to do now is I'm going to help you realize that this is -1 to the first power right there. And we have a property that says if we have something to a power times the same thing to a different power, you can add the powers together. So this becomes -1 to the n plus 1. Think about it. Now if I plug in 1, what do I get on top? If I plug 1 in here, what do I get? If I plug, a sub n. If I plug 1 in here, I get 1 plus 1 is 2. And -1 squared is +1. Now plug in 2. You get -1 to the 3, that's -1. So all we did was shifted our index over by 1. By adding 1 to n, we shifted it. Okay. I would like to give you your homework. Solve using elimination. This will be due on Thursday, yes. Come in before you go to Thanksgiving. Just come on in. 5x minus 2y. Trying to make sure these numbers are going to turn out nice for you. Check. I'll zoom this out so you can see it all here. Can you all make that out all right? Okay, let's do that as homework. We'll come in on Tuesday. We'll have our last day of class. We'll finish up the sequences and series stuff. And then that following Thursday, we have our review and then the final. Everyone have a good holiday. Be safe and ease up over there.